There we go. Alrighty. So yeah, 5.1 is trig identities. 5.2 also concerns trig identities, so we kind of lump them together. So with that, go ahead and grab your notes and let's get going. Trig identities. And so there are several types of trig identities. There's actually 3 types that we're going to talk about today, and then we're going to talk about kind of how to use them and get a lot of practice with using them over the next couple of days. You can expect a quiz for this probably next Wednesday sometime. We're only going to be quizzing over sections 5.1 and 5.2. And then we'll take some time for 5.3 after that, which also continues to deal with trig identities, but it's also more the solving of trigonometric equations in 5.3. So that's why we break it off from the rest and talk about it separately. So trig identities, here we go. The first kind of trig identity is the reciprocal identities. Reciprocal identities. So the reciprocal identities are all the sine, cosine, tangent, secant, cosecant, and cotangent, the ones that relate those. So, for example, cosecant is equal to 1 over sine. And secant is equal to 1 over cosine. Those tend to be the harder ones to remember just because cosecant sounds like it would go with cosine, but it doesn't. So remembering that still from back at the beginning of chapter 4, we need to bring that forward with us into this. We also have that cotangent is 1 over tangent. And then the same thing, but flipped, goes for the other way around. We could also use the fact that sine is 1 over cosecant. Cosine is 1 over secant, and tangent is 1 over cotangent. All right, so those are all the reciprocal identities, and those ones tend to be easy enough to remember once you start using them. Doesn't take a lot of deriving it or anything like that. Those tend to be ones that we remember from before, where cosecant is just sine flipped, secant is cosine flipped, that sort of thing. The second one, or the second type of trig identity that we want to be able to know and use, are the quotient identities. The quotient identities. Okay. So we knew from talking about the unit circle about at least the first of these quotient identities, or we've talked about it anyway. It's that tangent is equal to sine over cosine. So that's one we're going to use. And then the reverse of that is that cotangent is cosine over sine. Okay. So those are the main ones that we're going to work with first. There is one more class of trig identities that we're going to talk about after we do a couple of examples with the reciprocal and quotient identities. But I'll give everyone a minute to finish writing here, and we'll do some examples. Okay, so there's a couple things that we will want to be able to do using these identities. The first thing that we'll want to be able to do is use them to simplify expressions. So for this first one, if we saw something like, I don't know, cosecant times sine minus cotangent times tangent plus 3, or I don't know, anything like that, we would want to be able to simplify these expressions. So typically the first thing you want to do when you're simplifying an expression like this, if the only thing you're working with here is reciprocal and quotient identities, then the first thing you really need to do anyway is put things in terms of sine and cosine. So what I would do here is go, okay, cosecant is 1 over sine. And then I would use the quotient identities for tangent and cotangent, or you could use the reciprocal identities here. It doesn't really matter either way. But a lot of times it's more convenient just to put it in terms of sine and cosine and use the quotient identities for these. So we have cosine over sine, and then tangent is sine over cosine, and then we can leave the 3 alone. So then what happens here? Well, the sines cancel each other out, and we're just left with 1 for this expression. Here, the cosines cancel, and the sines cancel as well. So we're left with 1 for that expression as well, plus 3. And 1 minus 1 plus 3 is 3. So this would be the simplified version of this entire thing. So you could have something really ugly and long that simplifies down to 3 or 1 or 0, because we're just using trig identities to shrink it down. So that's one kind of thing that happens. Another kind of problem that we're going to want to be able to do, let's say that cotangent theta is 4/5. Maybe we want to find tangent of theta. Well, if cotangent is 4/5, we have the reciprocal identity relationship that cotangent is 1 over tangent and tangent is 1 over cotangent. So I know tangent is 1 over cotangent, which just means I need to flip cotangent over. So tangent is 5/4. That's kind of the simpler version of the next level of problem that we're going to do. So we've done so far simplifying an expression. We've done using a trig identity to find a value that's related to it. The other kind of question that we want to be able to do just using reciprocal and quotient identities is going to look very similar to this, except it's going to involve drawing a triangle to find a little bit more information and recalling a little bit of our right triangle trig. Okay, so for this one, we're going to be told that cosine is 1/4 and theta is between 0 and 90. So that means it's in the first quadrant. And we want to find tangent theta. Okay. So this one doesn't inherently, or it doesn't have to use trig identities here. This one's a little bit different in that it's a lot more like what we did back in 4.2, 4.3. That's and to the left of the 0. Yeah. So the information that we're given here is that if we're dealing with a right triangle, for example, with cosine being 1/4, then that means 0 and 90 being what our angles between means we're working in the first quadrant. So if I draw a generic triangle in the first quadrant here, here's theta. We know cosine is adjacent over hypotenuse, so if this is theta, adjacent is 1, hypotenuse is 4. To find tangent, we know tangent is opposite over adjacent, so we need to find the opposite side. So we would use the Pythagorean theorem to do that. So this is kind of like those coordinate problems that we were working with back in 4.2, 4.3. So we would go 1 squared plus b squared equals 4 squared. 1 plus b squared is 16. B squared is 15, so b is the square root of 15. So then, since tangent is opposite over adjacent, tangent of theta would be root 15 over 1, which is just the square root of 15. Okay. Any questions with any of the first three so far? Anything we want to go back to? Any numbers we're not sure where they came from? Number 2. So number 2 was just taking cotangent and flipping it to get tangent. So that one was a trig identity. Okay. And since we've kind of already done ones like number 3, except those were the coordinate problems, I'm a little bit more concerned with doing problems like 1 and 2 here, making sure that we can take things and break them apart into sine and cosine, cancel where we need to, or notice that something like cotangent and tangent are related, and we flip. How do we know what to do for number 1? That's the trick here. So when we do trig identities, a lot of this is going to feel like little strange puzzles of how we can get things to simplify. And so before I completely talk about how exactly you know what to do, I'm going to show us one more kind of trigonometric identity, because that's going to affect kind of our step process. So in general, though, if you don't recognize any of this third type of identity that I'm going to talk about, the first step would be to put things in terms of sine and cosine. Did a different thing for each side. So we kind of did the same thing for, I mean, there weren't really sides here because it's just an expression and not an equation. But in general, you want to take whatever you can and put it in terms of cosine and sine. So in this case, cosecant we know is 1 over sine. Sine's already a sine. And then cotangent and tangent, putting those in terms of sine and cosine instead. But yeah. So these will take a little bit of getting used to. But before we start getting used to them and doing a bunch of different examples and things like that, oh yeah, the note on the left put in terms of sine and cosine. Yeah, so before we start getting like completely into these, we do need to introduce one more type of trigonometric identity, and it's called the Pythagorean identities. The Pythagorean identities. All right, so our third and final type of trig identity, the Pythagorean identities, makes us think back to the unit circle. So I'm going to kind of show how we would derive the first Pythagorean identity and how we can get the, if you memorize that first one, you can find the other two from that first one. So if we've got the unit circle here, we know that the radius of the unit circle is 1. And if I were to drop this down and make a right triangle here, we knew that from the unit circle, cosine is x and sine is the y value, right? So if that's the case, then this distance here, this y distance, is sine, and this x distance here is cosine. And since we have a right triangle and we know the Pythagorean theorem, a squared plus b squared equals c squared, then we know that this side squared plus this side squared equals this one squared. So this yields this identity that sine squared plus cosine squared equals 1 squared, which is just 1. So this is the main Pythagorean identity. Sine squared plus cosine squared equals 1. And you are going to see this everywhere. You're going to use this a lot in math, especially when it comes later down the road to calculus and things like that. The Pythagorean identities tend to crop up. So this main one is definitely an identity that we want to recognize. Sine squared plus cosine squared equals 1. And it's a very convenient one to use. Because anytime you see a sine squared plus cosine squared, you can get rid of it and replace it with 1. So that's convenient. Then, if you know this Pythagorean identity, you can use it to find the other two Pythagorean identities. So let's take kind of this offshoot of it here. We know that sine squared plus cosine squared equals 1. So if I go through and I divide by sine squared for all of these, I divide everything by sine squared, here's what happens. Sine squared over sine squared, they cancel and you get 1. Cosine squared over sine squared. Well, if we think back to our quotient identities, cosine over sine was cotangent. So cosine squared over sine squared is cotangent squared. And then 1 over sine squared, well, thinking back to our reciprocal identities, cosecant was 1 over sine. So cosecant squared is 1 over sine squared. So this 1 plus cotangent squared equals cosecant squared is another one of our Pythagorean identities. Well, what if I took this thing, sine squared plus cosine squared equals 1, and instead of dividing by sine on everything, what if I divide by cosine squared on everything? Well, then we have sine squared over cosine squared, which is just tangent squared. Cosine squared over cosine squared is 1. And then 1 over cosine squared is secant squared. So this gives us our other Pythagorean identity, tangent squared plus 1 equals secant squared. Okay, so these are 3 different identities that we want to be able to recognize. The main one that you want to make sure you remember is this one, because if you remember this one, then you can derive the other 2 by dividing by sine squared or by dividing by cosine squared on all the terms. Okay. And you also want to sort of be able to recognize different rearrangements of these. like on this one, if I subtract cosine squared from both sides, we get sine squared equals 1 minus cosine squared. So anytime you see a 1 minus cosine squared, you could replace it with a sine squared if you want to. Or same thing, if you see cosine squared, you could have 1 minus sine squared. You could replace that with a cosine squared. Or here, we could rearrange these as well. You could get 1 equals cosecant squared minus cotangent squared. So anytime you see a cosecant squared minus cotangent squared, you could replace it with 1. Or cotangent squared would equal cosecant squared minus 1. Same thing goes here. 1 would equal secant squared minus tangent squared. Or you could have tangent squared equals secant squared minus 1. So those are basically all of the different arrangements of your Pythagorean identities. So anytime you see something with like cosecant and cotangent squared, or sine and cosine squared, or tangent and secant squared, you want to be on the lookout for a possible Pythagorean identity. Okay, I'm going to give everyone a chance to finish writing these. And then we're going to do some examples that involve all of our different kinds of identities and simplifying expressions. Okay, anyone still need this? All right, then let's do some examples involving all of these different identities. And I'm going to tell you right away, the thing that you'll probably find most difficult is figuring out where to start. And a lot of times, figuring out where to, there's not like one particular way to do these. So it's kind of figuring out your own way, trying something and seeing if it works. If it doesn't work, or if it makes it more complicated, then you try something else. There are some general things you can try that tend to make your life easier, but in the end, it's just kind of getting used to how these work and starting to see things and see how kind of how the puzzle works in general. So here we go. I think this is example 4. So our goal is to simplify these and get them down to as few terms as possible. So when we talk about simplifying trig expressions, kind of our goal, we want one term or as few as possible. Few terms as possible. So for our first one here, we're going to do secant theta minus cosine theta. And we're going to try to simplify that down to as few terms as we can. Okay, so first, the first thing I would try for is to see if there's any Pythagorean identities. If you don't see any particular Pythagorean identities, then you move on to reciprocal and quotient. So in this case, I don't see any Pythagorean identities. So what I would probably do here is then move on to reciprocal and quotient identities and put everything in terms of sine and cosine. So for this one, we have cosine already, but secant can become 1 over cosine. Okay. At this point, since we're trying to put things in as few terms as possible, I might try making a common denominator. So to get this thing a common denominator, this thing has a denominator of cosine. This thing has a denominator of 1. So to give this a denominator of cosine, I'm going to multiply on the top and the bottom by cosine. Because what that then gives me is we have 1 over cosine minus cosine squared over cosine. And then, since we have a common denominator, I can subtract on top and go 1 minus cosine squared over cosine. So now, we're back to seeing something with a cosine squared in it. So now I can think, maybe there's a Pythagorean identity here. So step 4 here is back to Pythagorean. We notice that from our Pythagorean identities, this 1 minus cosine squared is a rearrangement of it. We know that 1 minus cosine squared is equal to sine squared. So I can replace this. We have 1 minus cosine squared over cosine. This is equal to sine squared over cosine. And now we can continue simplifying just a little bit here. This is equal to, if I pull off a sine, sine times sine over cosine. And then we know that sine over cosine is tangent. So this is equal to sine times tangent. And this would be our simplified version. So secant minus cosine is equal to sine times tangent. A lot of these, we're going to look at them and go, oh yeah, that looks similar or simpler. On a lot of them, though, you'll also look at it and go, how is this any simpler than what I started with? And so a lot of the reason for why we go through this unit is not going to be super apparent until we get to the trig equations unit. Because a lot of times, until we can get things simplified, it's really hard to solve an equation. So this step of learning our trig identities and learning how to simplify them will help us out later. Okay. So again, these are the steps that I took to solve this. These are not always the hard and fast steps that you will take to solve each to simplify each trig expression. A lot of these things are things that we can kind of try along the way in any particular order. Or not in any particular order. And the way that we get better at these is by doing more and more of them. Any questions so far about this one? Any steps we don't know what happened? You know, things can kind of get lost. Anything we're not sure where it came from. Okay, well, let's try another. Next one we will do cosecant cotangent squared plus 1 over sine. We're going to simplify this. Okay. So for this one, and again, this step here might kind of seem like math magic, but, or like how the heck would you know to do this? But cotangent squared. Cotangent squared looks like something from a Pythagorean identity. And it is. And that's what we're going to use first. So if you look at your Pythagorean identities, cotangent squared, one of our arrangements of it is cosecant squared minus 1. So we're going to replace cotangent squared with cosecant squared minus 1. So instead, we're going to have cosecant squared minus 1. And then 1 over sine is equal to cosecant. So this is a reciprocal identity here. Then I'm going to go ahead and use the distributive property. We get cosecant cubed minus cosecant x plus cosecant x. Then negative cosecant and positive cosecant cancel each other out, and we're just left with cosecant cubed. And that is our simplified version. Okay. Another thing that will kind of help us in things like this is tomorrow when we start talking about verifying trig identities, where you'll be given actually two sides of an equation and you have to make the two sides look like each other. Because then you'll at least have a goal of exactly where we're headed. That's why just straight up simplifying trig expressions like this is useful up to a point, but unless you have some kind of a goal, it can feel a little bit pointless. So anyway, that's another example of simplifying a trig expression. Okay. Let's see. Let's do one more together, and then I'm going to have you guys try one. And then if we have time, we'll talk about one more thing. Okay. Cosine times tangent plus cotangent. Okay. Simplifying this. First, I don't see any particular cause for a Pythagorean identity. There's nothing squared in here. So there's not a lot I can do with Pythagorean identities at this point. So the first thing that I would do then is change these two into terms of sine and cosine. So we have cosine of x Tangent is sine over cosine. Cotangent is cosine over sine. So now everything is in terms of sine and cosine. The next thing I would probably do is the distributive property. So we get cosine sine over cosine plus cosine squared over sine. And then we might notice here that cosine and cosine can cancel. And we're left with sine plus cosine squared over sine. What I would probably do next is make a common denominator here. So this one has a denominator of sine, this one has a denominator of 1. So I want my denominator to be sine. So I'm going to multiply by sine over sine. And sine times sine is sine squared. And then we can add these two together. We get sine squared plus cosine squared over sine. And sine squared plus cosine squared is 1. So we get 1 over sine. And 1 over sine is cosecant. So this whole thing simplifies to cosecant. Okay. So for some of this, we can kind of see to an extent that there's a process. You look for Pythagorean identities, then you start looking at reciprocal and quotient identities if you don't see anything squared in there at all. Then we start looking at common denominators or distributing, things like that, trying to bring everything together into one term. And then simplifying from there, maybe we come back to doing Pythagorean identities. But also to some extent, there's not a whole lot of there's not specific concrete steps that you take each time. So these do take some getting used to, like I said. All right. Any questions from either of these two so far? Okay. The freedom in this is that if you try something and it makes the thing look worse, then you go back and you try something else. And the nice thing too is that there's not always just one way to do this. Sometimes there's multiple ways to simplify it. Your guys' turn to try one. We're going to do cosecant times sine plus cotangent squared. Go ahead and simplify that one. If I could make a recommendation, it would be to start with reciprocal quotient identities for sine and cosecant. But there's other ways that will work too. So let's see, when sine x plus sine x and the x goes away. Well, when you're adding fractions, you don't, I assume this is what you mean. When you add fractions with the common denominator, you don't add the bottom, you just add the top. Oh, no, you're right. The x should actually still be there. I just got lazy with my notation. Yeah, so it should be sine of x still. Yep. Thank you. All right. When you think you've got this simplified as far as it will go, type got it in the chat. Or when you're stuck. If you started off with going 1 over sine instead of cosecant, that might be a good choice. Or if you replaced cotangent squared with cosecant squared minus 1, that would also work. If you're looking to check your work, this is one way you could do it. You can go 1 over sine times sine. The sines cancel, you get 1 plus cotangent, which is one of your Pythagorean identities, giving you just cosecant squared. Did anyone do it a different way? Does anyone see a different way you could do it? Either way, you would have to do this part eventually, but you could have also replaced cotangent squared with cosecant squared minus 1. You got it the way I did it? All right. Yeah, this is kind of the way that was most clear to me. But you could place cotangent squared right off the bat. And then you would also still have to do this part, though. All right. So, let's see. We've got enough time. We're going to talk about one last thing. And the one last thing we're going to talk about kind of goes hand in hand with this. It's just a bit of multiplying with sine, cosine, tangent, and stuff like that. Because tomorrow we'll talk a little bit about factoring with it. So today we want to talk about distributing with it. So that's what we're going to talk next. And then we will get our assignment and talk about that. Okay. So you guys have seen like foiling or double distributing or whatever with like typical things like x minus 1 times x plus 1, that sort of thing, right? We've seen this. You end up with x squared plus x minus 1, which then gives you x squared minus 1. we're going to do the same kind of thing, but using sine, cosine, and tangent, and secant, cosecant, and cotangent, and that sort of thing. So it's going to look very similar to this. It's just a matter of kind of getting past sometimes the mental block that we get when we see something written a bit differently. So we're going to do, let's go with 2 cosine theta minus 1 times cosine theta minus 3. We're going to multiply these. Okay, so it's going to go the same way with double distributing and stuff like that it does on something like this. When I multiply here, 2 cosine times cosine is 2 cosine squared. 2 cosine times negative 3 is minus 6 cosine. Then negative 1 times cosine is minus cosine. Negative 1 times negative 3 is plus 3. Then to finish it out, you just combine like terms. We get 2 cosine squared minus 7 cosine plus 3. So this kind of looks like unsimplifying things. But tomorrow we'll talk a little bit more about like how you would take something like this and factor it. So we also want to be able to unfactor it, multiply through and things like that. So I'm going to have you guys try one real quick. And then we'll be done with new stuff. Three tangent x minus 2 times 2 tangent x plus 1. Go ahead, multiply this one. When you think you've got it, type "got it" in the chat. Carson's got it already. He's quick. You did this problem over 200 times in the summer because your mom made you IXL. I love it. Except doing it over 200 times, well, you get a lot of practice in, but might be a little bit of overkill. But it pays off at a time like this. Your mom sounds like a smart person. All right, Jasmine's got it as well. Awesome. Wherever you're at in the process, if you want to check your answer, you should get 6 tangent squared minus tangent minus 2. Okay. So that is the other kind of problem that we are going to do today. Time to talk about the assignment. Today's assignment is a worksheet. You actually, the assignment for the next several days is worksheets. Sometimes we'll do all the problems, sometimes we'll do some of the problems. Today's is only a one-pager, so we're going to do them all. The first 10 are matching. So you're simplifying these trig identities. The first couple are pretty simple, and then from there it gets a little bit more difficult with knowing what to do for each of these. But you're matching them to things over here. So at least you have some kind of a goal of what these things are supposed to look like at the end. So we're matching trig identities for the first 10. And then for the next, 12 problems, we're finding the products. So we're multiplying. If it's squared, make sure you don't just square individually the things inside. You actually have to multiply it by itself. So like cosecant x plus sine x squared, you'd have to go cosecant plus sine times cosecant plus sine. So don't forget that you have to write that whole thing out. Okay, so that is today's assignment. No IXL today, actually no IXL for a while, because I don't love their trig identity stuff at the moment anyway. So there's your homework. I know. Maybe we'll do a bit as a review or something like that, but they don't line up as well with what we need. So there's your trig identities assignment. I'll also post an exit ticket in a moment. If you have any particular questions, you want to work out a particular problem with me right now, stick around, or if you want more examples, stick around. Otherwise, you guys are free to go and work on your own. Bring any questions that you're wondering about with you tomorrow to class too, if you need to. See you all tomorrow.